Moving on to section 6.4, optimization problems 1, creating the model. For the rest of this chapter, we're going to be looking at optimization problems. If you can get this, you're golden. Test to be a piece of cake. Building on it a little bit. So it shouldn't be too much of a problem as long as you are up to date on what we did before. Problems. So we're going to take a look at all of this good stuff. So let's check this out. So this investigate the math. We're going to work on this as a class tomorrow. That's the first thing we're going to do is whip through this real quick. It's a toy company manufactures two types of toy vehicles, racing cars and sport utility vehicles. Because the supply of materials is limited, no more than 40 racing cars and 60 sport utility vehicles can be made each day. The company can make 70 or more vehicles in total each day. It costs $8 to make a racing car and $12 to make a sport utility vehicle. There are many possible combinations of racing cars and sport utility vehicles that could be made, but the company wants to know what combinations will result in the minimum and maximum costs and what those costs will be. So that's what an optimization problem is going to be all about, is determining minimums and maximums. It's going to help companies determine minimum costs, maximum costs, things of that nature, to help to determine so that there's no waste or that they're not wasting money or spending too much money or whatever the case might be. So we'll explore this a lot as we go along. We're just going to be building on what we already know. So like I said, we're going to whip through this problem wicked fast tomorrow, so come prepared to do that first, and then we'll do stuff. So we'll look at example 1 now. Creating a model for an optimization problem with whole number variables. The problem goes like this. 3 teams are traveling to a basketball tournament in cars and minivans. Each team has no more than 2 coaches and 14 athletes. Each car can take 4 team members, and each minivan can take 6 team members. No more than 4 minivans and 12 cars are available. The school wants to know the combination of cars and minivans that will require the minimum and maximum number of vehicles. Create a model to represent this situation. So now when we go to create these models, the graphing, the steps are going to go as such. We're going to add steps to move along. But for now, the steps are going to go like this. Step number 1 is going to be determining our variables. Since we're talking about minivans and cars, right here you can see the minivans and cars. We can say that M is minivan and C is cars. Any questions so far? No? Okay, let's keep going. The next thing we're going to do is determine the restrictions on the variables. And now, of course, we're talking about minivans and cars. We're probably not going to have a negative number or a fraction. We're talking about whole numbers here. So the minivan is going to be an element of the whole number system, and the car is going to be an element of the whole number system. So here we've got step 1, determining our variables, step 2, determining our restrictions. And what they're going to call step 3 is constraint. On your in your books on page 326, we can see the definition of constraint. It's a limiting condition of the optimization problem being modeled, represented by a linear inequality. So we were doing 6.3 and we were graphing. Step 3 was coming up with the linear inequalities. So when we talk about the optimization problem, we say constraints, it's the same idea. We're coming up with the linear inequality. Now in this case, we're going to talk about the constraints for the cars and the minivans. It says no more than 4 minivans and 12 cars are available. So we'll start with that. No more than 12 cars, no more than 4 minivans. So our constraint for the cars is that the C is going to be less than or equal to 12. And the constraint for the minivan is that our minivans are going to be less than or equal to 4. No more than 12 cars, no more than 4 minivans. But back at the beginning of the question, we saw it said something about 3. I thought I saw that somewhere, maybe not. But we have to come up with 3 linear inequalities because we have 3 different ideas going on. So the third one has to do with the number of people that can go. So each car can take 4 team members. each minivan can take 6 team members, but what we don't know right off the top of our heads here is how many team members there are in total, at least as a maximum. But the first thing it says is that each team has no more than 2 coaches and 14 athletes. So if there's 2 coaches and 14 athletes as the maximum for each team, that's a total of 16 people per team. It says 3 teams are traveling. So we can multiply this by 3 to determine that there's going to be a total of 48 people that are traveling. They're going to be traveling in the cars and the minivans. Car can take 4 people, minivans can take 6 people. So that's going to dictate what our next inequality is going to look like. So what we're going to do is we're going to say 4 people per car and 6 people per minivan has to be less than or equal to a total of 48 people. So here are the constraints or the linear inequalities that we're going to have to graph. The next thing we have to do, step 4, now the last thing we were doing, step 4, was just to graph it, but now we have to come up with something called the objective function. So again, on page 326 of your textbook, so we can see the definition for objective function reads, in an optimization problem, the equation that represents the relationship between the 2 variables in the system of linear inequalities and the quantity to be optimized. So the quantity to be optimized here today is going to be the number of vehicles. The way we can determine that is it always asks the minimum and maximum number of, and in this case, it's going to be vehicles. So the equation for that is going to be very simple. It's going to be the vehicles, the number of vehicles is going to equal the number of cars plus the number of minivans. As we move along, we're going to see that we're going to have to add coefficients in front of these variables in other questions. So if we're having a cost, for instance, you might have to throw the cost in there, or whatever the case might be. We'll see lots of examples as we move along. But for now, there's our objective function. Step 5 is going to be to graph it. Now, there's a lot involved when we go to graph these, as you have learned so far. So I've already got my graph labeled with the x-axis being our m-axis, our c-axis, our y-axis is c, and so we're going to have to graph each of these. So I'm going to make some space where I can do some steps over here right below the graph. So we're going to do the boundaries here. I'm going to call this step 5, the graphing. So the first one is c is less than or equal to 12. I'm just going to call that c equals 12 for the boundary of that. So we are talking about whole numbers only here. So whole numbers with equality as a possibility for all 3. So that means all 3 of our boundaries are going to be stippled green lines. So that first one where we say c equals 12, we're going to call that a horizontal line through this point, c equals 12. So we'll go here and there. Oh, I missed it. Just get rid of these. I went a little bit too high. Right there. Yep. So this is going to be our stippled green line for c equals 12. The inequality, c being less than or equal to 12, less than or equal to 12 means clearly we're going to have to shade below that line. Because it's whole numbers, we're going to be shading orange. So that's the first one, c equals 12. The second one, we'll just say it's m equals 4. So now we're talking about a vertical line right through m equals 4. Again, we're going to talk about green stippling because of the fact that we're looking at whole numbers with equality as a possibility. So there's the boundary point for m equals 4. The inequality was m is less than or equal to 4, so everything less than 4, so we're going to have to shade to the left of that line. We're going to take a look at our third inequality. So a nice way of graphing that would probably be, I don't know, determining the x and y intercept would probably be a pretty easy thing to do. So we'll extend our page, give ourselves some more room. 4c plus 6m equals 48. So to determine our c intercept, we'll go 4c, since m is 0, it's just 4c equals 48. Divide by 4 to get c equals 12. What happened to that? 12. C equals 12. For the m-intercept, c is 0, so it's just 6m equals 48. Divide by 6, and we get m equals 8. So we have a c-intercept of 12, an m-intercept of 8. Let's go up and do that. C-intercept of 12 right there, m-intercept of 8 right here, and we're just going to try and connect them if I can. approximately like that. Do our best. Now we have to determine our shading for that line. So I'm going to do that over here. This is still part of step 5 for the graphing. Keep it as neat as you can, especially Clark, please. So we have 4c plus 6m is less than or equal to 48. And what we want to determine is we can use the origin 0, 0 because that's not on that boundary point. So we can put 0 and 0 for m and c. So we add those up, multiply them out, we'll get 0 is less than or equal to 48. True statement. So for that boundary, that oblique boundary, we're going to shade below. Let's review our shading. For this boundary right here, we decided that we're going to shade below because it had to be everything less than or equal to 12. For this boundary right here, we're shading to the left because it had everything less than or equal to 4. And then for the oblique boundary over here, we just tested 0, 0, found a true statement, so we are shading below. So now there's one region that's going to be shaded 3 times. So I'm going to use my red marker for the orange shading. Of course, you guys are going to have red pencil crayons. You're going to shade it a beautiful orange pencil crayons, shade a beautiful color of orange. But this region here was shaded 3 different times. I'm shading it orange. Beautiful color of orange, kind of like the sunset. We're talking about whole numbers with equality possibilities, so we're going to have to stipple in here as well. So stipple on our whole number points. Yep. Looks good. Again, on page 326, we can see, bottom page 326, we're going to look at the solution of that graph really, really nicely so we can see the different layers of shading, if you will. So that's all optimization problems part 1 is going to be. It's nothing really new. This is just we're calling it something different now. I guess the only really new thing here is that we've come up with the objective function, and this is what we're trying to optimize. As we progress, we will figure out how to optimize that, where the minimum and maximum values are going to be found in the solution region, things of that nature. Let's see. The your turn question says, suppose that the greatest number of athletes changed from 14 down to 12 per team. It's asking how Juanita's model changed. Let's take a look at that. I'll put the marker down.
I defined the variables I needed for my solution. I used M to represent the number of minivans and C to represent the number of cars. Both M and C must be whole numbers because fractions and negative values don't make sense in this context. I wrote the 2 inequalities that Juanita used in her model. C is less than or equal to 12, and M is less than or equal to 4. I knew that these 2 inequalities would not change because they are not affected by the number of team members. I determined the greatest number of team members traveling if there are 12 athletes and 2 coaches on each team. Then I substituted this number, 42, into the inequality that Juanita used to relate the number of cars and the number of minivans to the maximum number of team members. Each car can take 4 team members. Each minivan can take 6 team members. The objective function remains the same. I sketched a graph of all 3 inequalities to represent Juanita's new model. Juanita's new model is similar to her original model. However, the area of the feasible region is smaller, and it includes lower values of C and M. This is reasonable, since fewer vehicles would be needed if there were fewer team members.
That's going to be it for example 1.